In this video, we're going to be talking about op-amps. An op-amp, short form for operational amplifier, is an electric circuit component which is responsible for amplifying voltages. We'll get more on what they do later on, but first let's see how does an op-amp look. In reality, an op-amp looks something like this. It's an integrated circuit that fits right onto our breadboard. You'll work with these in labs, but right now let's see how do they look in circuit diagrams. An op-amp drawn in a diagram is simply just a triangle with 5 connections. It has one inverting input indicated with a negative sign, a non-inverting input indicated with a plus sign, 2 supply voltages indicated with plus VCC and minus VCC. In a real circuit diagram, they'd be something like plus 5, minus 5, and we have one output terminal. An important thing to note is that our output voltage must always be in this range. Namely, our output voltage must always be greater than negative VCC, our lower supply voltage, and must always be less than plus VCC, our positive supply voltage. So now let's talk about what does an op-amp actually do. If we look in this circuit, we can see that our non-inverting input is connected to some voltage Vp, and our inverting input is connected to some voltage Vn. Our output voltage, which is what we're usually interested in when we're working with op-amps, is simply some amplification factor A times the difference Vp minus Vn. And our amplification factor A is usually on the magnitude of 10 to the power 6, which is huge. Now, if you think about it, even if our Vp minus Vn is something small, like 0.1 volts, our Vout is still going to be 10 to the power 5, which is almost always not going to be in this range. We never have supply voltages on the magnitude of 10 to the power 5. So what happens now? Well, this is something called saturation. When an op-amp saturates, there's 2 cases. Either it saturates positively or negatively. So when our output voltage is greater than our plus VCC, we can just consider our output voltage to be VCC. Whereas when our output voltage is on the lower end, when it's less than negative VCC, we say that our output voltage is negative VCC. To understand this further, let's take a look at this graph. This graph basically depicts the trend that I just showed you. Whenever our op-amp has Vp minus Vn small enough to where Vout is still in this range, it operates in what is called a linear region. That means that the output and the difference Vp minus Vn are proportional. But when Vp minus Vn gets to a point where it's large enough that Vout is no longer in this range, and Vp minus Vn is positive, we call this the positive saturation range. That means that no matter what our output voltage mathematically comes out to, the op-amp is only going to output a maximum of this plus VCC. Similarly, let's take a look at the other case when Vp minus Vn is negative, but the absolute value of it is still large enough to where our Vout is something very negative, which is lower than our negative VCC supply. In this case, we can say our op-amp is in its negative saturation region, and the op-amp would simply output negative VCC, even though mathematically we're finding it to be some very, very negative number lower than negative VCC. As you can see, unless Vp minus Vn is very, very small, this op-amp circuit is not very useful to us because it's almost always going to saturate. So let's find a way to make better use of op-amps. Let's consider this circuit over here. Now, some important things about this circuit. This is the type of circuit that you're going to be seeing in this class from now on. A circuit like this without a feedback path. As you can see, a feedback path is when your input is connected to your output. This type of circuit isn't commonly seen in this course. This one is the one you're going to be working with a lot more in class and in lab because it's a lot more useful. And let's see why. This circuit allows us to use these 2 ideal op-amp equations, which make life a lot easier for us when we want to use op-amps and do analysis on op-amp circuits. The first equation tells us that Vp is always equal to Vn. So let's define what Vp and Vn are. Vp is simply the voltage at your non-inverting input. So we can label this right here as Vp. And Vn is simply the voltage at our inverting input. The second equation tells us that the current going into each input terminal of the op-amp is always equal to 0. So let's define what these currents are. This would be our current IN, which is going into the inverting input of our op-amp. And this one right here is going to be our IP, which is going into the non-inverting input of our op-amp. For our first example, let's take a look at this circuit. The first thing we want to do when analyzing any op-amp circuit is write down our ideal op-amp equations. If you recall, they are Vp is equal to Vn and In is equal to Ip is equal to 0. So let's identify what is Vp, what is Ip, what is Vn, what is In. So let's see, this is our inverting input. So we'll call this voltage right here as Vn and the current going into it as In, which is equal to 0. Let's see, what's our voltage Vp? Well, Vp is the voltage at the non-inverting input, and Ip is just the voltage going into this, which is equal to 0. So now let's begin our analysis. We can easily find one of these two quantities. We can easily see what's Vp. This positive input, this non-inverting input, is simply connected to ground. And ground is our 0 volts. So we can just say Vp is equal to 0 volts. And referring back to our first ideal op-amp equation, Vp is equal to Vn. So this means that Vn must also be equal to 0 volts. So let's label this right here. Vn is equal to 0 volts. Or I can make it bigger. I can write 0 volts right here. This is the first step. Now let's use the fact that In is equal to 0. Let's assume that we have some current in this part of the circuit called I1 and some current through the feedback loop called IF. We can calculate I1 and we can calculate IF. But first let's do a KCL at this node to see what it gives us. So KCL, what does it tell us? We have a current I1 going into this node. So we'll say I1 is equal to, and it splits up into IF and IN. So I1 is equal to IF plus IN. And we know from our ideal op-amp equation that IN is equal to 0, which leaves us with the relation I1 is equal to IF. Now let's go ahead and calculate these, because we know the voltage at both ends of this resistor, and according to Ohm's law, if we know the voltage and we know the resistance, we can find current. Same applies for this resistor right here. So let's calculate I1 first. I1 is simply equal to the voltage difference across this, which is Vin minus Vn, right here, over R1. And we know Vn is equal to 0 volts, which is, so I1 will simply be equal to Vin over R1. Let's do the same thing for the feedback resistor and the feedback current, IF. IF is equal to the voltage across this feedback resistor, which is equal to Vn at this end minus our output, which we can label as right here as V out. So Vn minus V out over Rf. And let's plug in our Vn equals to 0, which we found, and we get 0 minus V out over Rf is equal to If, which simplifies to negative V out over Rf. So now we know I1 and we know If. But from our KCL, we found that I1 is equal to If. So let's set them equal to each other. V in over R1 is equal to negative V out over Rf. And we want to solve for V out, because in most op-amp circuits they're going to ask us what's the output voltage, or it's going to be something related to the output voltage. So let's solve for it. We'll say V out is equal to multiply both sides by Rf and multiply both sides by -1, which gets rid of the Rf and then gets rid of the negative sign, and we're left with V out is equal to Rf, negative Rf over R1 times V in. So what does this result tell us? Well, the first thing we can see is that there's a negative sign over here. And this means that whatever our input voltage is, our output voltage is going to be negative of that, times the ratio of Rf to R1. This is commonly known as an inverting op-amp. Another thing that we can see from this is a quantity called gain. Gain is equal to your output voltage over your input voltage. So if we calculate that for our op-amp circuit, we can see that V out over V in is simply equal to negative Rf over R1. So this was just the first example. As you can see that when we use our ideal op-amp equations and we go step by step, analyzing an op-amp circuit isn't too hard. Let's do one more. To analyze this op-amp circuit, we're again going to have to use our ideal op-amp equations. The first step is just going to be to write them down. So Vp is equal to Vn. In our second equation, Ip is equal to 0 and In is equal to 0. This can also be written as Ip is equal to In is equal to 0. It's the same thing. So now let's label these on our diagram. We know this right here is our node Vn, and we know In is equal to 0. And we also know that this is our Ip has to equal to 0. Now, this resistor may throw us off a little bit because we don't know where to put Vp. Well, realize that there's no current flowing in this branch of the circuit, which means that this resistor has no effect because the voltage across the resistor is V is equal to I times R. But since I is equal to 0, the voltage across the resistor is equal to 0, which means that anywhere in this branch we can consider as Vp, and this is simply going to be equal to our voltage Vin. And the reason being is we start at ground and we gain our input voltage Vin, and we don't lose any voltage across this resistor, and all that's going into our input terminal is Vin. So Vp is equal to Vn is equal to Vin. And as you can see, this relation just told us that Vn is equal to Vin. So now we know that this voltage right here is equal to V in. Now again, we want to do a KCL at this node of the circuit. So if we call this current I1 and we call this current IF, and we do our KCL at this node, we can see that I1 is equal to IF plus IN. The current going into this node is I1. The currents coming out is IF and IN, which is why we add them together. And from our second relation, we can see that IN is equal to 0. So we're left with the relation I1 is equal to IF. Now let's go ahead and calculate I1 and IF. I1 is equal to the voltage across this resistor R1. We know at this end of the resistor we have 0 volts, and over here we have V in. So let's go ahead and write that down. 0 minus V in over R1 is our I1, and we can simplify this down to V in over R1 is equal to I1. As for IF, we apply the same concept. The voltage across this resistor divided by the resistance will give us the current. We have V in on one end, and we can call this node right here V out. We have V out on the other end. So if we do V in minus V out over RF, this gives us our current IF. Now, using this relation we just established, let's set these two equal to each other and solve for V out. So let's do I1 is equal to IF. So negative V in over R1 is equal to V in minus V out over RF. Now it's just algebraic manipulation. Solve for V out, multiply both sides by RF. These cancel out, and we're left with negative V in times RF over R1 is equal to V in minus V out. And solving for V out, we get V in plus V in times RF over R1. And let's go ahead and bring out this common factor V in. That gives us V out is equal to V in times 1 plus RF over R1. Now, let's also go ahead and calculate the gain of this circuit. If you recall, gain is equal to our output over our input. So if we divide both sides by V in, we get 1 plus RF over R1. Now let's quickly compare this to our previous circuit that we analyzed. And you can see that they both share this common factor RF over R1. But this circuit has 1 plus RF over R1. But the key difference is that our inverting op amp had a negative sign. So you can see that our V out is going to be negative some ratio times our V in. Whereas in this circuit, we see that V out is just equal to V in times 1 over RF plus over R1. So what this means is whatever our sign of V in is, V out is going to share the same sign. So this tells us that this is a non-inverting op